All right, so I hope you can hear me. All right, please confirm if the audio and video quality are fine. All right, good morning to you all. And today, as we already know, we're going to discuss how to solve the state space equations. Okay, so that is something we're going to do today. And as I told you, that state space modeling is a very systematic technique. Okay, and it's a systematic technique and it helps to have a systematic solution. Okay, because uh, if we want to implement it using a computer program, and if the process of the solution, the process in which we obtain the solution, or rather the solution itself, is a very systematic thing, okay, in that case it becomes really helpful for a for if we want to implement this using a computer program. And you will soon see that it's very easy, rather much easier than the Laplace transform model when it comes to implementing it using a computer program. On top of that, as we already know, that state space modeling can handle any type of system. Okay, the system does not have to be a continuous time linear time invariant system. Okay, it could be a discrete time system, it could be a nonlinear system, it could be a time variant system. Okay, it does not have to be a particular type of system in order for state space model to work. Okay, so you can have any type of system, any complicated type of system that cannot be simply handled by the transfer function modeling approach. Those systems can be handled using the state space modeling approach. But also you have to keep in mind that at least in this course we are only studying the state space modeling related to continuous time linear time invariant system. So we are restricting ourselves to simple use cases. Okay, so we're not just jumping into very complicated system, jumping into describing very complicated systems. That is something we're not going to do here in this course, at least. All right, so it appears as though that people are coming and leaving. Okay, so please stay here, don't just leave yet. All right, all right, so as usual during this discussion, if you have any query, feel free to ask. All right, so we described that earlier, that we described that if we have an LTI system, okay, and if it had a particular input, and the input is in this nomenclature is given by u, and it had an output, so the output is given by y. These are all functions of time. Then we realize that we can construct something called the state space model, which is a very systematic, structured, well structured model. Okay, so we are saying this is a continuous time LTI system. Okay, all right. And also, most importantly, we described something called the states for the system. So states was an internal vector that describes the internal properties of the system, some internal behavior of the system, some internal dynamics of the system. For example, we described that if we have a mechanical system, then we describe the internal dynamics by describing the position of objects, okay, the displacement of objects, so and then the velocity of objects, then the other particular object, for example, okay, acceleration of objects, and so on. Okay, so these variables do represent, these state variables so called do represent some internal variables. Okay, so this is used to describe the internal dynamics, right? And again, we actually described how to we actually learned how to construct the state model out of state space model, out of transfer function models, and vice versa. And this is actually written in this way. Okay, and here you see that this x actually simply denoting that this is the vector. All right. All right. So many people has already left. Okay, by just putting up their name on here, they have just simply left. That's a good sign that you don't want to listen to this, but doesn't matter really. Let me talk anyway for those who are listening. Okay, so I would keep on asking questions, so please keep on responding. All right, so the state equation, so it is actually described, the systems are described using two equations. Okay, the state equation and the output equation. Okay, and the state equation is this equation. The derivative of x is given by this, and the output equation is this. All these underlines, these are indicating that these are either vectors or matrices. Okay, these are vector matrices, any of those, right? So again, u is the input, y is the output, and x is the internal state. Okay, and x dot is the derivative of the internal state, so that's the derivative of the state vector here. All right, so again, we are going to solve a few problems after this once we actually try to figure out, once we figure out the solution of this differential equation. But remember, x is a vector quantity here, x dot is also a vector quantity, b, a, c, d, all these are matrices, and u is also a vector quantity, y is also a vector quantity. So instead of trying to solve this differential equation, because strictly speaking, this is not an easy differential equation to solve. Okay, let's try to solve this differential equation instead. Okay, let's recall something that we probably have studied in our school levels. Okay, say we want to solve this differential equation, a very simple differential equation that looks like this. X dot is equal to ax plus bu. Now notice that here I have written scalar quantities, so these are just scalar functions. Okay, so if I write it explicitly, that becomes dx dt. So x obviously is a function of time. Okay, and that equals ax, x is obviously also a function of time, plus bu. Notice here that x is a function of time, so let me just write it that way instead. Okay, here also x is a function of time, so let me write it that way. And b ut, here u is also a function of time, so u is the input to the system. Okay, so that's the description here. All right, so this kind of a differential equation is called a linear first order differential equation. So this differential equation is known as the linear first order differential equation. Linear first order ordinary differential equation, right? And you probably know how to solve this differential equation. Let me just bring this to the left hand side and try to figure out what happened. Okay, so this is derivative of, so this is, let me just write it as x dot, that indicates the derivative, minus ax, okay, and that's equal to b minus axt, let me just write it that way, and that's equal to b ut. All right, so let me just so I just brought this to the left hand side here. All right, and this is a very simple first order ordinary differential equation, and solving this is not a very challenging task. Okay, so in order to solve this, we actually need to multiply the both sides of the equation with something called the integrating factor. But instead of bringing that up in this context, what I'm going to do, I'm going to multiply this with a factor that helps us combine these two factors. That helps us combine these two factors. Okay. Okay. All right. So, but before we actually do any of that, let me ask you this simple question. So, for example, you probably already know the product rule of differentiation, right? Product rule of derivatives. So, let's say I have something like this, e to the power minus at times xt. Okay, and I want to differentiate this with respect to t. Okay, question is, what is the result of this derivative? And the result is very simple to understand, that we are going to first differentiate this, keeping this constant, and then differentiate this, giving this constant, and add them up. That's the result, right? That's the product rule. So let's first differentiate this and keep this a constant. All right. So if I differentiate that and keep that keep the rest as a constant, so what we get is e to the power minus at times x dot t, because that's the derivative here, and then put a plus sign, and we have to now differentiate this keeping this a constant. Now derivative of this is minus a e to the power minus at, right? So that becomes minus a e to the power minus at, and obviously the rest of that is kept a constant. Now you notice that if we take e to the power minus at and factor it out of this, then what we have is x dot t, and here we have minus a xt. Notice that this is exactly what we have here. This is exactly what we have here. Okay. So what we are doing right now, we are multiplying both sides of this differential equation with e to the power minus at. Because if we do so, let us just write this first. If we multiply both sides of this differential equation with e to the power minus at, all right, all right. So then we can actually write, instead of the entire thing on the left hand side, that can be written simply as the derivative of e to the power minus at xt, right? Right. Please tell me if you find it difficult to understand. If you find it difficult to understand, please tell me right now. Okay. All right. So let's consider this entire thing. Let's consider this entire thing to be something. I don't know. Maybe let's assume that to be zt. Okay. Let's write that down as zt, something like that. Okay. Okay, that's also a function, simple. Okay. All right. And let me just write it here. Let zt to be equal to e to the power minus at xt. All right. Now let's try to solve the rest here, because this is not a very difficult thing to solve right now. Okay, because all I need to do, I need to bring this differential dt to the right hand side and then try to integrate. So immediately I have derivative of zt. So it's like dz. It's simply writing it will be just simply dz. Okay, it's just like that. It is dz, and when I integrate this, it will be simply z. But let me just write it in proper terms anyway. So this is derivative of zt, not the derivative, the differential of zt. And here on the right hand side, I have e to the power minus at b ut times dt. All right. Now I have to integrate this, obviously. Now when I integrate this, let's see, I have to integrate it on both sides. So on the left hand side, I have, just hold on, let me just increase the number of pages that are available. All right. So this is that. It is just simply writing dz, okay, and writing the integral of that. So it's simply going to be z, okay. And on the right hand side, we have this. Okay, we have e to the power minus at b ut dt. All right, e to the power minus at b ut dt. Any confusion there? No confusion, right? I hope. All right. Now try to notice that when we integrate like both sides of a differential equation, we need to put a constant here, right? We need to put a constant, and that constant will be taken care of ultimately when we put certain initial conditions in this, right? But instead, let me just get rid of this and make this integrations definite integrals rather. That way we can actually get rid of the arbitrary constant as well, right? So there are two possible ways in which we can achieve that. So first is that we solve this differential equation, put these values, particular values, and then figure out what should be the value of this constant. Okay, and then we can actually convert these these integrations from this indefinite integrals to definite integrals. Okay, and from there we can actually proceed. All right. So let's say this is a differential equation with respect to time, right? This is a differential equation with respect to time. Okay, and here notice that time varies from 0. So what we are saying is that this system is not only just a continuous time linear time invariant system, this is also a causal system. I should rather say it's a causal continuous time linear time invariant system. And this differential equation that we are having here, we are assuming the system to be causal. Okay, we are assuming the system to be causal, which means that the impulse response of the system will be a causal signal, and thus if the input is also a causal signal, the output is also a causal signal, which means the impulse response sequence, or rather impulse response, only appears after t equal to 0. Okay, so when t is less than 0, the signal is 0. Okay, the impulse response is 0. Similarly, the input is also like that. So when t is less than 0, the input is also 0. So this kind of behavior is called a causal behavior. So right. So under these scenarios, the output is also a causal signal, which means when t is less than 0, the output is also 0. So everything starts at t equal to 0, something like that. But again, keep in mind that this is not a very bad assumption, because you can assume any moment to be t equal to 0, right? Right now can be t equal to 0 for you. Okay, 10 minutes later could be t equal to 0 for somebody else. Okay, so we are starting from t equal to 0 to t equal to t, something like that. We are going up to a certain amount of time, right? Now, of course, writing this sort of notation like t equal to t is a very bad notation, because we say that we are actually replacing the limits with the same variable, right? So here t is the variable of integration here, and we're just replacing it that way. So it's like writing this sort of integrations, like okay, it's like somewhat like writing like that. So it indicates that we are starting from x equal to 0 and then going up to x equal to x. Ultimately, we are going to integrate with respect to x and then replace x with x. Okay. Ultimately, we are going to get the answer in terms of x, but it's bad. It is a bad notation. Instead, what we should write, instead of calling this x, we should put a dummy variable instead. Maybe we should just call it y. That way, the ultimate answer will be the same. Okay, but we are now removing the ambiguity of just writing x equal to x. That's a very bad thing to do. Okay, so this will still give me the same answer, but it will actually be cleaner mathematically speaking. Okay, so that is exactly what we do here. Instead of writing t and integrating with respect to t and then putting certain values of t and writing t equal to t once again, so that's a very bad notation. So instead of writing that, let's put a dummy variable. Let's call it tau. Okay, let's call it tau, and let's put a dummy variable, because ultimately we are going to integrate with respect to that, and we are going to substitute the values, right? So ultimately we are going to substitute the values, so it won't matter. Okay, so this writing tau does not matter, because ultimately we are going to substitute its values with the upper and the lower limits. Okay, so ultimately the result will be in terms of t, so it does not matter. Okay, just keep that in mind. And when tau is equal to 0, so notice here we have something called the 0 initial conditions. So here we are integrating this. So what is the initial condition on this? So initial condition is z0, and when this is equal to t, that's the output. So when the value of time is t, then obviously the output is zt. Now when the value of time is 0, when the output is 0. So just like that. Okay, just a very simple notation once again. All right, so that by doing this definite integral trick here, we have actually converted this possibility of writing this arbitrary constant. Rather, we have actually completely given up on that, completely removed that possibility of writing an arbitrary constant here. Okay, because we don't need that anymore, because this is now a definite integral. Okay, solving this differential equation. All right. So please again tell me if you are facing difficulty understanding this. All right. Now this is a very simple differential equation. If you see, notice very carefully, it's a very simple differential equation, because I mean it's like just like dz I told you, right? It's like just like dz. So it is just something like dz, integration of dz. So it's just z. Okay, and of course it has upper and lower limits. Okay, so let's put the limits. So the lower limit is z0 and the upper limit is zt. So obviously it's like zt minus z0. That would be the answer, right? Now what about the right hand side? The problem that we unfortunately are facing right now is that we don't know what is about the right hand side, right? We don't yet know what is about the right hand side, because you have to understand that this very thing is unknowable. How to do this integration is unknowable until we know the value of this input, right? We don't yet know what function we have as the input, right? What kind of signal we have as the input. So that way we don't yet know how to actually write down that in a simpler form. Okay, if we knew a certain value for bt, okay, sorry, certain value of the input, then in that case we could actually solve this differential equation easily. But since we don't know that yet, we cannot write that. So we just have to write the right hand side as it is. So it's a integration on e to the power minus a tau b u tau d tau, where tau varies from 0 to t. See, I'm not writing tau equal to 0, tau equal to 2, because it is assumed that it is happening with respect to tau. Okay, tau is being replaced. So that is something that is being assumed here. All right. Now, of course, let's put the upper and the lower limits. So we have zt minus z0, and on the right hand side, once again, have this. Right, any confusion there? I don't think any confusion should be there, right? So with that being said, let's now go back to where we assumed the zt here. This was the assumption for zt, right? This was the assumption. So zt was equal to this. This is the assumption we took. Since zt is this, okay, of course there we are going to write this. And what about z0? Z0, let's put t equal to 0, and that's going to be e to the power 0, that's going to be 1, and it is just x0, right? You see? So here, let me just replace what we have here. So that's going to be e to the power minus at xt minus x0, because x0 is the value of z0 and zt is essentially that, because that is what we assume. Okay, and obviously the right hand side is as usual, so that's the integration from 0 to t on e to the power minus a tau b u tau d tau. All right, and let's bring this to the right hand side. Okay, let's bring that to the right hand side, and if we bring that to the right hand side, it becomes got it? Not a very difficult thing once again. And now we just need xt. You see, we wanted to solve a differential equation, right? We wanted to solve a differential equation, and we had a differential equation with respect to xt, right? So that was the dependent variable. We wanted to solve this and figure out xt, and that is exactly what we have right now with us. Okay, xt is, now let's multiply both sides with e to the power at, right? So xt will be then on the left hand side, and here we have e to the power at x0 plus e to the power at integration from 0 to t e to the power minus a tau b u tau d tau. Okay, you see, when we wrote tau here, it also removes the ambiguity with respect to this t, because this is irrespective of this integration here. Now this is something very similar to this discussion happened in your signals and systems classes as well. The reason why we actually do this kind of dummy substitutions there. All right, and notice that this integration is happening with respect to dummy variable tau. Okay, so this can be brought inside. This integration can, this vector can be brought inside, and that way we have e to the power at x0 here, and plus we have 0 to t, that integration, and here we have e to the power. Now of course let's think about this. So this is essentially e to the power at times e to the power minus a tau. That becomes e to the power at minus a tau, and that is simply e to the power a t minus tau, and that's here we have b u tau d tau. All right, that's xt. So this is the solution of the state equation. This is the solution of the state equation because we have finally solved the state equation, right? But we are not there yet because we want to find out the output of the system. So this is the solution of the state equation. Okay, if somebody asks you to find out the solution of the state equation, that is the final result. Okay, so of course in the scalar form, right? We haven't yet gone to the vector form here, but we are going to just write that shortly. Solution of the, let me just write it when we actually write down the vector form. Okay, so this is the solution for this differential equation. X dot is equal to ax plus bu when all of these are scalar quantities, right? Now here we wanted to actually solve this differential equation where so all of these are vector quantities. Okay, matrices a and b are matrices here, and x and u, these are vector quantities. Okay, so all you need to do is to just write this in a proper form, okay, in the proper way, and this can be done due to some properties of mathematics here. Okay, therefore let me just write it down this way. The solution to the state equation so here we just take this equation and replace everything with the corresponding vectors and matrices. So this is going to be e to the power a t. Now you might say, okay, what is e to the power a matrix? What is e to the power a matrix? We are going to actually learn that shortly as well. So that's x0, okay, plus this integration e to the power a, that's t minus tau, and here I have b u tau d tau. All right, so that's the solution of the state equation. Now notice something very important here. This is not the state equation for a particular system. Okay, this is not the solution of the state equation for a particular system. This is the solution for all possible systems that are causal, linear time invariant, and continuous time. Causal, continuous time, linear time invariant. Okay, so if we have a causal, continuous time, linear time invariant system, then the state equation will always be looking like this, and the solution is always going to be looking like this. Which means that we have not only solved we haven't solved this equation for a particular system, we have solved this equation for every possible system. Okay, and soon, right now, I mean few moments later, we are going to actually see an example where I practically solve a problem, I have a system, and we are going to actually solve that system, rather solve the state model of that system in order to find out the output of the system. Okay, all right, but before we proceed, let me think about the output, because these are just the states. So this is the states. Okay, this is giving me the states solution in terms of that. But also notice that the output equation gives me that the output is equal to C times X plus D times U. Now obviously out of this, what you need to do, you need to just put the value of xt because we have just solved for it, right? Therefore yt is equal to, now let's put this C matrix here, and here let's bring this entire thing here because that's xt. Right, and that's plus d u t. Okay, right? I don't think any confusion should be there. All right, now let's multiply these accordingly. So because this C will be pre-multiplied everywhere, so let's multiply that. So C e to the power at x0 plus C times this integration 0 to t e to the power a t minus tau b u tau d tau plus d u t. Okay, I mean, okay, understood what you are asking. So you are asking me to solve this differential equation, but this is not a differential equation. I told you that this is just the state space model is one differential equation, one algebraic equation. Okay, the state space model, this is the state space model. Okay, for any continuous time linear time invariant system, this is the state space model, and this one is the differential equation. We need to just solve this, and this is just an output equation, and when we solve for this, we get x. We get xt, right? We just put the value of xt to get the output. Okay, that is exactly what we did. We calculated xt and we just put the value of xt here in this equation to get the value of yt. Because the second equation, like the output equation, which is known as the output equation, it is an algebraic equation, right? This is the state equation, which is the differential equation. But the second one, which is the output equation, is just an algebraic equation. We need to solve for x from this equation and put it back here, and that will give me the solution. Okay, final solution here. So there is no solving the second equation, right? We just solve the first equation and put that value of xt, the solution of the state, into this. So now this is the very fundamental result. Okay, this is so fundamental in fact. We just have to box it up here. Okay, but before I do that even, so you see there are three distinct parts. Okay, again, what is yt? Yt is the output of the system. Once again, recall that this is corresponding to a system that appears like this. This is corresponding to a system that appears like this, and which was modeled very systematically using the state space approach. You see, I have a system that has ut as the input. You see ut is appearing in these scenarios here, and yt is the output. All right, yt is the output. And you notice very carefully is that it is the output here. So this is the equation for the output here. So if I know the input, and if I know these matrices A, B, C, D, again the matrices that describe the state space model, okay, then I can actually find out precisely the output. Now you notice very carefully that the output has three distinct parts. Okay, the output has three distinct parts. Okay, all right, some would say the output has two distinct parts, but I will say that there are three distinct parts. Notice very carefully that this is one distinct part in the output, and this is also the second distinct part of the output, and this is the third distinct part of the output, right? So this is not very hard to notice, right? Now here you see that this is a part of the output. So notice that u is the input, right? So notice very carefully that here, just hold on. All right, but please tell me if you understood the explanation here. Anyway, so there are three parts, yes, here in this equation, right? And as you can see, um, there are three distinct parts here. And look at the first part here. So when we look at the first part, we specifically notice that this is devoid of any input function, right? Input function is ut, but this part of the response does not have any input. Okay, is not related to what input was there, right? Even if input is 0 here, okay, even if the input is 0 here, you would see that this part will still remain, right? It is completely devoid of any input function, right? But what is this x0? This x0 is the initial condition of the system. Notice that when we write x0, okay, let's go back to this. So when we write x0, that is just this vector here. This is x10, x20, x30, and so on. So it is the initial condition of all the corresponding states. That's the initial condition function. Okay, so this is representing the initial condition, and this thing is representing the response to initial conditions. Okay, and this response to initial conditions is known as the natural response of the system. Okay, so this is the natural response of the system. Okay, so this is the natural response of the system, because you see that this part of the response of the system, that comes from not the input but naturally from the system itself. Even if the input is 0, this will be there. Just hold on for a second. All right. So again, as I was saying, that this part of the response comes out naturally, which means that it is irrespective of what input was there, what input was given to the system. Okay, so this is due to the initial conditions. Okay, the initial states that was there before I even had given any input to the system. Okay, so this is completely devoid of any input, and that part of the response is known as the natural response, right? Right, and obviously this part of the response, as you can see, the next part of the response here, it involves the input, and also here it involves the input, right? So these two parts of the response requires that we have the input there. Now if the input is 0, then these two become 0, right? These two parts of the response become 0 if the input is 0, right? So now you have two particular things that have a dependency on the input. So two particular parts of this response that have dependency on the input, but they are completely devoid of any initial conditions. So whatever initial conditions we have for this system does not matter. Okay, does not matter. So these two taken together, sometimes referred with a particular name, these two taken together. Okay. Taken together, these two are sometimes called the forced response. Now, why do you think it's called forced response? The answer is very simple, because the input is called the forcing function. Okay, input is often called the forcing function. Basically, the input, when the input appears in the system, we are kind of forcing the system to respond. Okay, that's why this is called forced response, right? So we have one part which is called the natural response, we have another part which is called the forced response. And out of the forced response, we have two particular divisions there as well, two particular parts of the forced response as well. So this particular part of the response is due to the very system itself. Okay, because of the very system itself. And here you see, this is kind of a measurement or feed forward fact. Okay, this is not going through the dynamics of the system. Okay, so this is part of the dynamics of the system, but this is not part of the dynamics of the system. All right, so this is just directly being calculated out of that. So this part that is being directly calculated out of this is called the measurement. Okay, measurement or feed forward. This is called sometimes called feed forward, or sometimes called measurement response. Just keep in mind this is simply called the feed forward response. Okay, and this part of the forced response is called the system response because the system is involved here directly, dynamically. Okay, that's called the system response. Or sometimes some people just directly call this one the forced response. Okay, so there are certain differences which call it the input output response. Okay, so yeah, you can call it the forced response. Sometimes it's called the forced response, or maybe just call this system response rather. Okay, and this is sometimes called the input output response. Yeah, your assumption is perfectly all right. The system parameters are independent of the input and independent of the initial conditions. Input and initial conditions. So A, B, C, D, these are completely irrespective of the inputs and initial conditions. Yes, we are going to solve a problem that will actually solidify the fact. Okay, it will actually completely cement the idea that what you are saying is absolutely correct. Okay, these parameters, system parameters, by saying system parameters, I mean A, B, C, and D. These are completely irrespective of what initial conditions are, what inputs are there. It is completely irrespective of those. Okay, so system response, this is also called the input output response. Okay, so I think it's not a very difficult thing to see. All right, so these are the three parts of the response, and taken together, one part is the natural response, and this whole thing is sometimes taken together as the force, called the forced response. Okay, all right, so let me just solve a particular example here. Again, of course, we have actually given you, I have given you, rather shown you particular examples earlier, but there is a problem, particular problem here. What is the problem? The problem is when we actually look at this very carefully, we have e to the power at. That's a very weird thing, right? If I ask you, have you ever seen a matrix in the power of a function? Okay, this is like a matrix in the power of a function, like e to the power at in the exponent here, right? So let's first tackle this part here. Okay, let's first tackle this part here. So what is e to the power at? We know e to the power at is a very simple thing, right? It's a exponential, okay, right? But how do you even calculate that? You calculate that using a very simple expression which says it is equal to e to the power at, 1 plus at by 1 factorial plus at whole square by 2 factorial plus at whole cube by 3 factorial and so on. Right? Any confusion there? So that's the Taylor series for this exponential, right? E to the power at, right? And you already know that. Okay, so that's not a difficult thing to ask, and that's not a difficult thing to understand either, right? Right. Now the thing is, it can be shown that this e to the power at also satisfies the same relationship. It is like, now instead of 1, it will be I. Okay, I is the corresponding identity matrix. So if it is a 3 by 3 matrix, this is going to be a 3 by 3 identity matrix. So if A is a 4 by 4 matrix, so this is going to be a 4 by 4 matrix. Okay, so I plus, so this is going to be A times T by 1 factorial plus this is going to be A times T whole square by 2 factorial. This is going to be A times T whole cube by 3 factorial. Now this might seem absurd, but this is not. This is exactly, absolutely true in this regard. Okay, this is true in this regard. Okay, you got this, right? But the problem still persists. The problem is how do I find this out, right? So if I have to calculate this e to the power 80, do I have to keep on doing this infinite series? The answer is sort of yes and no. Okay, if you want to do this infinite series, it's good, because this is how you implement this in a computer. Okay, when you want to implement this equation in a computer program, you would want to do loops and things like that. So this is a fantastic way of writing this, because even as humans, you cannot so easily multiply matrices and not alone, let alone square them up, cube them up. But if you give it a if you make a computer program to do these things for you, like squaring a matrix, cubing a matrix, and adding them up like that, it's very easy for a computer, right, to calculate all these things. This is so systematic for a computer, not so much for us human beings. Okay, not so much for us. So for us, let's figure out how to actually think about this in a slightly different way. Okay, in a slightly different way. All right, and whenever we have something like this, what comes to rescue is something called Laplace transform. Now, obviously, you see, notice very carefully that this differential equation, this system was causal, continuous time, linear time invariant. We could use the transfer function approach. The only thing that we would lose by doing the transfer function approach is this natural response part, because the natural response part will not be there when we take the transfer function approach, because in the transfer function approach, we assume zero initial conditions. Okay, and since we assume zero initial conditions, this cannot be there, this is assumed to be zero, so this natural response cannot be found from the transfer function approach. So that is the only thing we have to lose here if we wanted to use the transfer function approach, because the system is otherwise continuous time, linear time invariant, so all the conditions for having a transfer function model are there already. Okay, so those are there. Okay, so let's try to apply the transfer function. So here again, let's take this one, the simple example here. Let's apply Laplace transform. So if I calculate the Laplace transform of this e to the power at, and again we are assuming it's like e to the power at ut. Okay, we are assuming that t is greater than or equal to 0, because causal systems, right? We are assuming causal systems. So here, under that assumption, this is equal to 1 by s minus a, right? 1 by s minus a. Any confusion there? I don't think so, right? So this is like s minus a whole to the power minus 1. Any confusion there? I don't think so, right? So which means this e to the power at is kind of the Laplace inverse of s minus a reciprocal of that, right? So s minus a whole inverse, and that's e to the power at. So not a problem, right? And now let's extend this to this. Let us extend this idea to that. Now, so when we extend this idea to that, so when I say that, okay, fine, what is the Laplace transform of e to the power at? The same idea applies, except for the fact that I cannot write something like this, like s minus a. Those sort of things do not work. Okay, but look at this. This is like s minus a. Okay, but unfortunately, you see that s is a scalar quantity and a is a matrix. Here, it's a 3 by 3 or 4 by 4 or 2 by 2. It's a square matrix, right? And you already know, I already told you earlier, that what if I have something like this and I want to factor out a. So if I want to factor out a, you see that I factor out a and then I don't have 1 minus b, right? I don't have just 1 minus b, I have something called I minus b, right? And just like that, this instead of being s minus a, this is going to be just si minus a. Okay, just to keep the possibility of subtracting this. Again, all these things do happen in the state space, because this I is the identity, right? This I is the identity. So here it's like equivalent to writing 1. Okay, it is right equivalent to writing 1. So once we have that, then from there, can I say that the inverse Laplace transform of si minus a whole inverse, that is equal to e to the power at, right? So that is exactly how we are going to approach this problem. We are going to actually solve this using this Laplace transform approach, because this is perfectly doable if we have a computer. Okay, I mean, this is perfectly doable if we have a computer, or rather if we are writing a computer program, because in that case, diving into Laplace transform opens that Pandora's box once again, right? So we don't want to use Laplace transform when we are actually writing computer programs for this sort of things. But when we are manually calculating these things, then Laplace transform is a very viable option, right? So that is something we have actually taken care of here, right? So there is one more thing regarding this equation here, regarding this part of the equation. So let me just tell you that, let me go back. Yeah, so this is the equation here, right? So this pretty much looks like, so think about this integral here. Simply speaking, think about that part of the integral. Okay, let's talk about this part of the integral, because there is something I need to just talk about right now, because that will come in handy when we actually try to solve a few things. Practically speaking, we can always do substitutions in differential equations, right? We can always do substitutions, and let's do a particular substitution in this differential equation as well. Okay, so notice that we can do some substitutions like t minus tau. We can assume that to be, let's say, p. Okay, and obviously tau is the variable here. Notice that t is a constant here for this, so this is becoming minus d tau as dp. All right, so simply d tau becoming minus dp, not a problem there either. All right, and what about the limits? What about the limits of this differential equation here? Upper limit and lower limit. So here we have the limits of tau, and here we are gonna have limits of p. Okay, all right. So tau, when tau is 0, what about the value of p? When tau is 0, value of p is so tau is 0, value of p is t, and when tau is t, the value of p is 0. So the limits are from t to 0. So I have e to the power ap b u, and instead of tau I would have t plus p, right? Tau will become t plus p, sorry, t minus p, that becomes dp, sorry, with a minus dp, right? So d tau is minus dp, so let's put the minus sign here, and since we have a minus sign here, we can get rid of that by just reversing the limits here. E to the power ap b u t minus p dp. But notice very carefully that this p is once again a dummy variable, right? This p is once again a dummy variable, so it could be replaced with any other value, right? Any other variable name. So why not just write tau once again? All right, why not just replace tau? So you see, we started with this expression and it is exactly equal to this. So let me just let that sink in. So this is 0 to t, this is e to the power a t minus tau b u tau d tau. If we integrate this, the result will be exactly the same as this integral. So sometimes what happens, to simplify our calculation, we would rather do this integration instead of this integration, whichever suits us, right? Because these two are going to give us the exact same result. So with that being said, let's get back to this originally. Okay, let's get back to this, because we are going to write another one here. Okay, what we are going to write, that it could be also same thing. That's yt. Here we don't have anything else. C e to the power at x0 plus c times this integration. Only change happens here. So instead of writing e to the power at minus tau, I would just write e to the power tau, e to the power a tau, and this is going to be b u t minus tau d tau. Same thing, exactly same thing. It is still exactly having the same value as this one. So whatever value of this one I calculate will be the same as this one I calculate. So this will exactly be the same. Okay, there won't be any changes whatsoever. So you can calculate it according to your wish, and depending on the particular scenario, whichever gives you simpler calculation, that one you take. All right. So enough with this example, derivations. Let's solve a particular example. Okay, let's solve a particular example. So we have been developing mathematical models for systems for a very long time here, and we also discussed developing simple state space models out of transfer function models. Let's do one of those. Okay. So let's say we have a system. That has been described with a particular transfer function. Right? So that has been described with a particular transfer function, and let's say the transfer function is, say, 2s plus 3 divided by s square plus hold on. Let's say it is 3s plus 2. Instead of writing this, let me just write it as 5s plus 7. All right. Now let me say that let's convert this to a state space model, right? Now I believe you recall how to convert this to a state space model. I'm not going to teach it right now because correspondingly it can be very easily understood once you understood the previous classes. So I hope you understand how to actually do this. And by just looking at it, you are supposed to be able to convert it to an equivalent state space model. All right. So this is again in the phase variable canonical form, and this is going to be 0, 1, minus 2, minus 3. All right. Yeah. And this is going to be x plus. This is a single input, single output system. So u would be a scalar quantity, y is also going to be a scalar quantity. So we have 0, 1 here. Okay. So u is a scalar quantity. And this is the state equation. So this is a differential equation describing the state. And y is also a scalar quantity. And this is going to be 2 and 7. Okay, and this is going to be x. And obviously d is 0 here. Okay, so this is A, this is B, this is C, this is D. And these 4 matrices, they describe the system completely. Okay, so now let's find out the solution. Now, instead of saying just find out the solution, let me just introduce the signals here. Okay, we are trying to find out, question is, find the, you see, I do not need the transfer function model at all. I mean, this was just for your reference. Okay, this is just for your reference. Find the output of the system when the initial conditions are, so that's called x0. X0 is essentially x10, x20. Okay, and say this is describing a damped pendulum, maybe something like that. Okay, so initial conditions, so let's say this initial condition is something like 1 and 0. Okay, so I have given this pendulum something like a initial position but not initial velocity. Okay, initial conditions are this, and the input is a unit step. So input is a unit step. Okay, so now notice very carefully once again that if I just want to calculate the output to this input, unit step input, all I need to do is to multiply this with 1 by s, which is the Laplace transform of the output, input, and take the inverse Laplace transform. I need to multiply this with 1 by s and take the inverse Laplace transform, and that will give me this response to this input, response to this unit step input. Okay, you got this, right? But we also want to calculate the response to these initial conditions, right? And we also want to avoid this sort of things here, sort of calculations here. So just keep in mind that we could just multiply this with 1 by s, which is the Laplace transform of the unit step input, and take the whole thing, invert it to get the output. Okay, right? So again, let's do this solution here. So we have A, B, C, D, these 4 matrices. So x1 is position, x2 is displacement, position, displacement, same thing. Displacement is position, from the equilibrium condition. So we had a sort of an equilibrium condition, maybe some a place where the system was initially relaxed. So the position when everything is initially relaxed. Okay, and so if I pull it up to a certain distance out of that, so thinking about a pendulum, so this is the initially relaxed position, and if I move it a certain angle here, right, that be an initial displacement. So which is also the position with respect to the initial with respect to the equilibrium condition here. Okay, so you can call it displacement, position, whatever. It's the same thing. Right? When we say position, it obviously calls for a reference point. Okay, you can only measure position with respect to reference. But when we say displacement, the reference is not required. Right. So with that being said, so let's try to first instead of actually solving this and writing out everything all at once, let's try to figure out this e to the power 80. Okay, let's try to figure out this e to the power 80. And how do I figure out this e to the power 80? By using this equation. Notice very carefully that this is one of the most important things, even though this is not how you do it in using a computer, because computers do not like this sort of equations, because this involves Laplace transform, which is not a very computer friendly thing. Okay, which is not a very program friendly thing. All right, so I need to calculate this e to the power 80 first of all, and I'm going to explain why the particular features and particular behaviors of all these functions. Okay, later on in the next class, very next one. So think about this e to the power 80. Now this e to the power 80 is known with a very special name. Okay, it's called the state transition matrix. It is itself a matrix. It is called the state transition matrix, and I'm going to explain that why it is called the state transition matrix in the next class. Okay, because if I wanted to explain this in this class, what would happen is that the entire class will be over with only theoretical discussion, so which I did not want. All right, so e to the power 80, we know it is the inverse Laplace transform of Si minus A whole inverse. Now we could use the infinite series expansion and do this, but we are trying to avoid that. All right, so let's take Laplace inverse of Si. Now what is Si? Si is I is 1001, so Si is S0 0 S minus, what is the matrix A? A was 0 1 and minus 2 minus 3. All right, and we have to take the inverse of that. So it's a bad thing already. Matrix inverse of that, and then take the Laplace inverse of that. So there are two inverses happening here. So we are taking the Laplace inverse of this thing. Now subtract these. So this is S, this is minus 1, this is 2, and this is S plus 3, and the inverse of that. All right. Now it is not a very difficult thing to actually invert a 2 by 2 matrix. I mean, if it was a 3 by 3 matrix, in that case it'd be very difficult to actually, not very difficult, but it is comparatively more difficult. Okay, so let's take the inverse of this. Now when we actually take the matrix inverse of something like A, B, C, D, it's a very simple thing. The result is 1 by AD minus BC, and here it is DA minus B minus C. You have probably studied this already, right? So here so this is the determinant. So this is the determinant here, right? We just write that down accordingly. So you know what? Bring this to the left. All right, so this is going to be the determinant, 1 by the determinant, I mean 1 divided by S times S plus 3 minus of minus 1 times 2, so that's plus 2. All right, and here we have to have that particular inverse. So here just the cofactor matrix correspondingly. So this is going to be S plus 3, this is going to be S, this is going to be 1, this is minus 2. So we have taken care of the inverse here. Any confusion up to this point? Right? No problem there, I hope. But here you see Laplace inverse of what do we have? Here we have 1 by s square plus 3s plus 2. Notice that this looks awfully similar to the denominator of the transfer function. We will come back to this in our next class. You see that this is awfully similar to rather the same as the denominator of the differential equation, right? Sorry, I mean the transfer function, right? So it's not a very difficult thing to now think about, right? So here, let's bring this, write that down here once again. All right. All right, so we have this right now, but we actually need to take the inverse here because we need to actually be able to solve this. So here we have to bring this. So this is a scalar quantity, so this will divide all of them. So instead of writing all these here, let me just write that down properly. So this quantity now becomes s plus 3 divided by s square plus 3s plus 2. This is becoming 1 by s square plus 3s plus 2. This is minus 2 by s square plus 3s plus 2. This is s by s square plus 3s plus 2. Got it? All right, so that's the set of equations here. Right now I have to take the Laplace inverse. And how do I take the Laplace inverse? Just take the individual Laplace inverse of all the terms here. So we have 4 terms, take the individual Laplace transforms of all the terms here, right? All right, so but before we even do that, we have to somewhat simplify this. And now notice that the denominator, notice that again, keep in mind that this calculation will not be there if we want to implement this using a computer, because when we are implementing this using a computer, we would just do this infinite series. Okay? Because we are calculating it to the over 80. That's the objective here. We are just struggling with that so far. So here in the denominator, we have this is s square plus 3s plus 2. That's like simply s plus 1 times s plus 2. And I chose that particular problem because of this, because I want this to be a very simple one. Okay, as simple as possible. All right, and as such, the numerator can be, so let me just write that down here. So that's s plus 3. So this is like 2 times s plus 2. So numerator here, that's like 2 times s plus 2 minus s plus 1. So that's a very simple calculation by which we can actually do a partial fraction expansion, because we want to have to do a partial fraction expansion. All right, and here similarly we have the same thing here, s plus 1 and s plus 2. And don't worry, in your exams at least you would get very similar examples, like very similar problems where the calculation is not that difficult. So again, you can see I can write down the top in terms of factors of the bottom things in the bottom, right? Here we have the same thing. It's like s plus 1 times s plus 2, and here that's going to be just I think 2 s plus, that's going to be 2 s plus 1 minus 2 s plus 2. You see, once again, in terms of the factors of the denominator, we have written the numerator. All right, and this is going to be s plus 1, same thing, s plus 2, and here the numerator is that, so we can actually write it as 2 times s plus 1 minus s plus 2. So that's the thing. Now here we can very easily take the inverse Laplace transform. That's the most laborious thing that is involved in this one. Okay, but again, I told you that when we are actually solving this using a computer, the computer won't even bother doing all this. All right, so take the inverse Laplace transforms, all these things individually. But before we again do that, let's try to split these quantities into proper forms. Right, so this one becomes this factor divided by this thing. So accordingly, this 1 by s plus 1 will limit. So this, so let's just do this splitting up here. Right? So let's pull them apart. So that's going to be 2 by s plus 1 minus 1 by s plus 2. So this one is going to be 1 by s plus 1 minus 1 by s plus 2. This is going to be 2 by s plus 2 minus 2 by s plus 1, and this one is going to be 2 by s plus 2 minus 1 by s plus 1. Right, now taking the inverse Laplace transform is a breeze, very easy thing. So all you need to do is take the inverse Laplace transform of all these individual terms here. So this is still a 2 by 2 matrix, huh? Keep in mind. So this is 2 e to the power minus t. Now of course all of them have ut, but I'm just going to write, after all this I'm going to write just this, indicating that other than that this is becoming 0, right? Because everything, all of this will have ut multiplied. So here e to the power minus 2t, and this is e to the power minus t minus e to the power 2t. Here 2 e to the power minus 2t minus 2 e to the power minus t, and 2 e to the power minus 2t minus e to the power minus t. Got it? So under that condition, so that is e to the power at. So we have successfully calculated the most important thing that is required here. Okay, we have successfully calculated e to the power at. Now once we are familiar with these things, I mean, this is not a very difficult, challenging task. Okay, so once you are done with that, let's get back to the solution. Okay, so this is the type of solution we are going to use right now. Remember that d is 0 in this particular example, so don't worry about that. We have to worry about these. Okay, we have to worry about these. So let me just write down. Therefore, the output yt will be yt, which is equal to c times those factors, right? C times, yeah, c times e to the power minus 80. So we have calculated e to the power minus 80, then x0. So let's put all the values here. Okay, so what was the C matrix? Let's bring this one here. So what was the C matrix? This was the C matrix. So 2 and 7. That's like 2, 7. Okay, then e to the power 80. Of course, e to the power 80 is this. Then x0. Now what is x0? That's the initial condition, and the initial condition has been given for this particular example as 1, 1, 0, and that's the natural response. That's the natural response of the system. Notice very carefully. That's the natural response of the system. All right, and plus the forced response. Once again, we have C. That's 2, 7. Okay. All right, and now we are going to actually use this second form here. Okay, second form here. So we're going to do this integration e 0 to t, and now here we have e to the power a tau and bu, like that. So let's just write it down, that integration from 0 to t. Now I have e to the power a tau. Now this is e to the power at. This matrix is e to the power at. Now how do I convert that to e to the power a tau? Simply by replacing this t with tau. By simply replacing this with tau correspondingly, I now have e to the power a tau, just like that. Okay, right? Then we have B matrix here, because of this, once again, that was the solution. So e to the power, we have written this e to the power a tau, then B ut minus tau, right? And what is the B matrix for this system? B matrix is this. Okay, this is the B matrix. So that was 0, 1. And u t minus tau, d tau. And that's the forced response because d is 0 here. Now, once again, notice that the input is a unit step here. Input is a unit step. So this ut is truly ut, right? So that's a unit step here. This input is the unit step. Now, obviously, the limits of the integration are from 0 to t. So tau is from 0 to t. So here, the internal factor here is positive. So which means that at least within these limits, this is equal to 1, right? This is equal to 1. All right. So this is equal to 1 for all the intents and purposes. So let's take care of these matrices. See, these matrices are constants. These matrices are constants, which means this can actually go inside this integration, right? The integration completed will forget about this really. Okay, so let's simplify these matrices, I mean these multiplications. So here for the first part, for the natural response part, 2, 7, and let's do this multiplication here, and that's obviously very simple. So you see, notice the dimensions here. So this is a 2 by 2 matrix and this is a 2 by 1 matrix. Multiplication is possible because these two are the same and the resulting dimension is 2 by 1. Okay, you understand the dimensions, right? So out of that, you notice that this multiplication, when we do that, so the result will be 2 by 1. So again, multiplying this with this and this with this. That's how the multiplication works, right? So when I multiply this with this, so obviously 1 times this, 0 times this, so obviously that 1 remains. So that's going to be the first factor. And when I multiply this with this, so 1 times this and 0 times this, so that 1 remains. So overall, these two are the things that will ultimately remain. So this will become a 2 by 1 matrix because of that multiplication. All right, so that multiplication is now over. Okay, and now write down the plus sum symbol here and think about the same thing happening here. So let's bring this 2, 7 inside. So that's going to be 0 to t, and let's bring this 2, 7, that matrix inside. And here we are doing a very similar multiplication here. So this is once again a 2 by 2 matrix. This is a 2 by 1. So this multiplication is possible because these two dimensions are matching. Resulting dimension would be this. So this is going to be once again a column vector like that. This is going to be a 2 by 1 matrix. And obviously multiply this with this and this with this. So when I multiply this with this, I am multiplying this with this. So that is the thing that will remain. And here when I'm multiplying this with this, this multiplies with a 1. So these two will remain, right? Here in this particular example, this is what is happening. Now in other examples, you might find that the calculation might be slightly easier. In some other calculations, you might find the calculations are slightly difficult. So again, depending on what kind of problem you received, a particular example that you received, and again, this is 1. Okay, depending on the particular values, this might simplify to simpler examples or more difficult examples. But keep in mind that this is the natural response, this is the forced response. We still have two parts of the response intact. Okay, and this can be found once again by just multiplying the original transfer function with 1 by s and taking the inverse Laplace transform. All right, so here we just have to do this multiplication. So this is 2 by 1, this is 1 by 2, right? What am I saying? This is 1 by 2 and this is 2 by 1. Multiplication is possible because these two dimensions are matching. Resulting dimension is 1 by 1. Okay, which means the result is a scalar quantity, and it has to be because the thing that we are finding out, so the left hand side is a scalar quantity, so the right hand side will have to eventually become a scalar quantity. So So this is 2 times this plus 7 times this. Okay, so let's do that calculation. So here we have 2 times this and 7 times this. So that means we have 14 minus 2. So that's 12 e to the power minus 2t. And then we have 4 and minus 14. So that's going to be minus 10 e to the power minus t. So if I have mistaken during the calculation, please let me know. And plus, regarding this integration 0 to t, here also something similar happens here. This again becomes a scalar quantity. So here 2 times this minus plus 7 times this. So hold on. Yeah, just hold on for a second. Did I write it correctly? Okay, same thing, right? So it's gonna be 14 minus 2. That's gonna be 12. The thing is, whenever I'm doing this sort of calculations by hand, my brain automatically hangs. I hope I have done the calculation correctly. I sincerely hope so. Because as I told you, I do not do these calculations anymore manually. All right, seems very difficult. All right, so make sure that this calculation is fine. So once again, this is the natural response and this is the forced response, right? These two are the parts of the responses for a system. And we have already calculated the natural response, so let's bring that in. Because that's the end of the calculation there. And plus, we have to now do this integration here. Not a very difficult job in that front. So that's going to be 12 by minus 2. So that's going to be minus 6 e to the power minus 2 tau. And that's going to be 5. So that's going to be 5 plus 5 e to the power minus tau. And the limits are from 0 to t. All right. And that's equal to all right. So and that's going to be plus. Now obviously put t and then put 0. So when I put t, I get 5 e to the power minus t minus 6 e to the power minus 2t. And when I put 0, I get minus 6 plus 5, right? That's minus 1, obviously, and that becomes plus 1 eventually, right? Because of that minus sign. So this simply becomes plus 1. All right, and all of these are valid when only when t is greater than equal to 0. So everything should be multiplied. So that's t greater than equal to 0. So ultimately, therefore, the output of the system is 12 e to the power minus 2t minus 10 e to the power minus t, okay, and then plus 5 e to the power minus t minus 6 e to the power minus 2t plus 1 for t, given that t is greater than equal to 0, right? And this can also be written by just simply saying that this is times ut, where u is the unit step. So this is the unit step. The same thing here, indicating that this condition is met here. Okay, all right. And these two, once again, this one represents the natural response of the system. And this one represents the forced response of the system. and taken together, they give you the output of the system. Now, what you saw is a very systematic approach, and this systematic approach is very easy to implement using a computer, because I mean, this is not very easy to implement using a computer, keep in mind. So we need to calculate e to the power at, and a computer would actually use this method rather. Okay, so if you want to write a computer program, you would rather use this method. And in fact, if you use Python, MATLAB, Scilab, any of these, they would inherently implement that methodology to actually calculate e to the power at. With that being said, these are the parts of the response. But let's go back and look at this transfer function once again. Okay, if I just wanted to calculate the step response, okay, so that was the transfer function. If I just wanted to calculate the step response, in that case, we could have simply considered the input, which is, say, for example, x input is, for example, ut, which is the input unit step. So input is simply 1 by s, the Laplace transform of the input. So let's say us is 1 by s. We could have just multiplied that, and the output of that Laplace transform of the output would be this. All right, and you could have taken the inverse Laplace transform, and you could have just calculated yt. But this yt, when you take the inverse Laplace transform of that thing, okay, that yt will be only this part. That is the one thing I wanted you to notice. So when you actually calculate this according to this, the output that you obtain would be only the forced response. So the natural response will be gone if we are using the transfer function approach. We cannot calculate the natural response using the transfer function approach, because in the transfer function approach, the very definition of the transfer function approach requires that we have zero initial conditions. And if we have zero initial conditions, how can you even have a natural response? Okay, so that's the final result. All right, and later on we are going to talk about how natural response tells you everything that is there to know about the system itself. Once again, that's a very important notion that we are going to learn in our future classes. And in the next class, we are going to actually talk about the deeper details regarding e to the power at and other facts about the state model. All right, and as a home, so I believe you understood the calculation here. So again, to keep you busy with some calculations, let me give you another problem. Okay, and this time around, I will just write down the state space model and ask you to actually solve this, find out the solution. Right, a system is given by, and while I am writing this, if you have any query, just ask. Okay, all right, a system is given by this equation. So once again, x dot is equal to, now this is a very simple one. You don't have to worry about what the transfer function might be. That is none of your concern right now. Then I'm simplifying this and say d is 0. Okay, d is 0, does not matter. So question is, find out the response of the system when the input is a unit step and the initial conditions are, which is given by x0 obviously, and that indicates that this is just x1 0, x2 0, this initial condition is 1 1. So that'll be your homework. You would have to calculate this response, right? Ultimately, I want yt. Okay, and you should also keep this in split format. See, I could have just added them up. I could have just simply added them up, and finally I could have written something like this. You notice very carefully. Just there is just one more thing I need to mention here. As I brought this up. Okay, I could have just added them up, and the final solution would actually be like this. So minus 5 e to the power minus t plus 6 e to the power minus 2t plus 1. So that would be the final solution, but this includes the natural response and the forced response together, and ut obviously indicates that before t equal to 0 everything was 0, but we haven't done that. Okay, but ultimately if somebody asks you what is the final solution, that should be the answer, really, right? The simplified form, right? Just keep that in mind. But this does not show you explicitly what is the natural response and what is the forced response. Now ultimately this is the response. Okay, just keep in mind. All right, so that's your homework for before the next class. I mean, please do this before the next class. All right, you would get some more insights once you solve this sort of problems. All right, so that's the end of today's discussion. I hope you don't have any more questions, because if you did, you would have already asked me anyway. But still, I would wait for just 1 minute, one more minute before you before I actually end the stream here. All right, so since you don't have any more questions, thank you very much. I will see you on the next one.